improve the performances of the glass units, several treatments were developed to modify their thermo-optical properties. The aim of this video is to describe the thermal and optical phenomena involved in the glass radiation interactions, in order to introduce specific glass products and their main applications. Firstly, it is important to describe what happens to the solar energy during the interaction with the glass panes. Glass is commonly considered fully transparent, but it interacts differently depending on the incident radiation wavelength. From a macroscopic point of view, depending on the radiation wavelength, once the solar radiation hits the outer face of the glass, part of the energy can be directly transmitted in the indoor environment, part can be reflected, and part can be absorbed by the glass pane. Then the absorbed part increases the temperature of the glass, which re-emits in forms of long-wave radiation the energy in both indoor and outdoor environments. The ratios of these three components, transmitted, reflected, and absorbed, to the total incident solar radiation define the transmittance, reflectance, and absorptance factors of the glass, which are usually reported with reference to the incident wavelength. This behavior can be summed up into two representative values, one adopted for the thermal analysis and one for the daylighting analysis, called respectively solar factor as F or G and visible light transmittance, VLT. The solar factor is the ratio between the total radiant heat entering the room through the glass and the total incident radiant heat in the whole spectrum. According to this definition, the numerator includes both the energy directly transmitted and the component absorbed and re-emitted in the room. Instead, the visible light transmittance considers the ratio between the transmitted light flux and the incident light flux, limiting the analysis to the visible part of the spectrum. Considering this dependency on the wavelength, it is fundamental to describe the solar energy spectrum to understand the performance of the glass. The solar radiation that reaches the Earth is composed by different wavelengths, which can be grouped in three main components. Ultraviolet radiation, between 280 and 380 nanometers, corresponding to nearly 3% of the total solar energy. Visible radiation between 380 and 780 nanometers, which corresponds to nearly 42% of the total energy. And infrared radiation over 780 nanometers, nearly 50% of the total energy. The transmittance, reflectance, and absorptance factors of a glass are usually represented in a graph where the different ratios between incident and transmitted, reflected, and absorbed fluxes are reported for wavelengths comprised between 300 and 2500 nanometers. Starting from these premises, the behavior of a specific glass can be described through its whole spectrum or simplified by using its solar factor and visible light transmittance. A clear glass can be characterized by a spectrum like the one represented in this slide, where the glass transmittances are reported as a function of the wavelengths. Overall, the solar transmittance is quite high along the whole spectrum, including both visible and infrared radiation. This behavior results in a very high solar factors, around 0.7, 0.8 in this example, and a very high visible light transmittance, around 0.8 or 0.9. Nevertheless, in many climates, during the summer season, the amount of incoming solar radiation should be controlled to avoid the room overheating, mainly in highly glazed envelopes. To that end, tinted glass can completely change the transmission spectrum, reducing the transmission at every wavelength, reaching lower solar factor but also lower visible light transmittances. The color of the tinted glass strongly affects the value of these parameters. For example, in these graphs are around 0.3 for the solar factor and 0.2 for the visible light transmittance. Nevertheless, the visible light is a fundamental parameter for the indoor environmental quality. Hence, it is often preferred to have higher visible light transmittances. To that end, the so-called selective glasses allow for the use of thin metal coatings to reduce the transmittance at high wavelengths while keeping the high transmittance in the visible field, as shown in this graph. It follows that the solar factor is low, 0.4 in this example, while the visible light transmittance is higher, 0.7 in this example. As explained in the previous slides, only a part of the solar radiation enters the building, depending on solar factor and visible light transmittance of the glazing unit. In this example, given the solar spectrum in yellow and the glazing unit with its transmittance diagram, only part of the solar spectrum is allowed to enter inside the building. Parts of the solar radiation entering in the room is absorbed by the material and object in the room and gets re-emitted as infrared radiation. But due to the low transmittance of the glass at infrared, the radiation gets trapped inside the room, thus raising the temperature of the room. Hence, it is important to pick the right type of glazing depending on the climate requirements. Using coated glasses allows to improve the management of the visible and thermal radiation. The low E coated glass located on the inner glass pane can reflect most of the indoor long wavelength thermal radiations, allowing to keep the indoor heat within the thermal zone, reaching excellent thermal insulation and high occupants comfort. Usually, they come with the qualities of excellent light transmission and low reflection, which allows maximum light penetration through the glass while providing low thermal transmittance and good clarity. On the contrary, the solar control coatings located on the outer glass pane can reflect most of the outdoor long-wave radiations, while visible radiation can easily pass through the glazing, as previously described for the selective glass. This behavior allows to reduce the incoming thermal radiation, preventing the summer overheating, while ensuring good daylighting and overall comfort. Many other coatings are available, and the specific products such as photochromic, thermochromic, electrochromic can also provide dynamic behavior, allowing to change the glass properties according to external stimuli to maximize the winter and summer benefits. As shown in this lecture, a conscious design of the glazed envelope cannot neglect the window's thermal-optical properties. Choosing the right glass and the right coatings can maximize energy efficiency and users' comfort, providing sustainable and comfortable environments, also in extensively glazed envelopes.